In the world of manufacturing, the quest for perfection is this relentless, never-ending journey. But what if perfect actually means two completely different, contradictory things? Today, we're going to look at how a team of researchers used an incredible digital toolkit to decode the secrets hidden inside a simple block of steel. What they found was a fundamental conflict, and a pretty revolutionary way to solve it.
All right, let's get into it. Here's how we're going to break this down. First, we'll talk about the steel itself. Then, we'll look at the seriously smart toolkit these engineers brought to the table. After that, we'll walk through the actual experiment they ran, and then, this is where it gets really good, we'll confront the conflict they uncovered. We'll see how they found an elegant way out, and finally, we'll zoom out and look at the bigger picture.
Okay, so the mission begins. The challenge was this: take a really common material, EN8 steel, and machine it until it's just about perfect. But here's the catch. In the world of precision engineering, that word perfect is, well, it's tricky. It's way more complex than you'd think, and it's hiding a major contradiction.
So first up, let's meet our main character, EN8 steel. Now, this isn't some fancy, exotic metal. It's a total workhorse. But don't let that fool you. This stuff is basically the hidden backbone of our world. We're talking about the high-stress parts in everything. Gears, axles, you name it. Seriously, if there's a machine out there moving under a ton of pressure, there's a really good chance you're relying on something exactly like this.
So, these researchers were chasing two different kinds of perfection. On one hand, they wanted the absolute minimum surface roughness. A finish that is just flawlessly smooth. But on the other hand, they wanted the absolute minimum circularity error, a shape that is geometrically perfectly round. Seems simple enough, right? Two goals. The problem is, trying to get both at the same time, well, as they were about to find out, that was going to push them into some pretty impossible territory.
So how do you even begin to tackle a problem like this? I mean, you can't just guess. These engineers didn't just walk in and start cutting metal at random. No way. They deployed this powerful trio of methods, a really specialized toolkit that's basically designed to find order in all the chaos.
First up in their toolkit was something called the Taguchi method. The best way to think about this is like a master strategist. It creates a smart blueprint for how you're going to run your tests. So instead of just doing 1,000 random experiments and hoping for the best, it designs a small, super efficient set of experiments that are guaranteed to get you the most critical information with the least amount of work.
Next, they brought in ANOVA, which stands for Analysis of Variance. Now, if the Taguchi method is the strategist, then ANOVA is the forensic detective. After you've run the experiments, ANOVA comes in and just meticulously sifts through all the data. Its job is to separate the really important signals from all the background noise. It's the thing that points and says, that's the factor that's actually making a difference.
And then there's the secret weapon, the genetic algorithm, or GA. This thing is something else entirely. It's inspired by natural selection, evolution. So it doesn't just analyze the data you already have. It actually breeds new solutions. It runs through millions and millions of possibilities, constantly tweaking and refining its answers, basically evolving its way toward the absolute best possible outcome. It's pretty wild.
So, armed with this three-part analytical arsenal, the researchers were finally ready. It was time to stop theorizing and get into the lab. Okay, so this table shows you exactly what they were testing. These were the variables they were messing with. You've got three main things: how fast the steel part is spinning, that's the speed. Then, how fast the cutting tool moves across it, that's the feed rate. And finally, how deep the tool cuts into the metal. For each of those three things, they tested 3 different levels, which set up the whole framework for their experiment.
And this is where that Taguchi method really shows its genius. You see, if you tried to test every single possible combination, it would take forever. But that smart blueprint called for just 27 specific trials. That's it, just 27 tests were all they needed to get the data required to unlock the whole system's secrets. Super efficient.
So, they ran the 27 trials. They got all their data, they fed it all to their detective, ANOVA. And as the computer started crunching the numbers, something really weird happened. They didn't get an answer. They got a paradox, a fundamental conflict that was buried deep in the physics of how this all works.
I mean, the question was supposed to be simple, right? What are the optimal settings? What's the one perfect recipe that gets us the perfect result?
Well, for that first goal, getting a perfectly smooth surface, the data was crystal clear. It said go with high speed, a low feed rate, and a deep cut. Boom! A simple, clear recipe for smoothness.
But for the second goal, perfect roundness, the data pointed somewhere completely different. It gave them a totally contradictory recipe. Medium speed, medium feed rate, and a shallow cut. The exact opposite in some ways.
And right there, that's the conflict. It's a total tug-of-war. The settings you need for a perfectly smooth surface will absolutely ruin your perfect circle, and the settings for a perfect circle will destroy your smooth surface. It seems like the two types of perfection just can't exist at the same time. You can't have both. Or can you?
This is it. This is the moment they deployed the secret weapon, the genetic algorithm. It's made for exactly these kinds of impossible situations. It's literally built to solve problems where there isn't one single best answer, but instead a whole landscape of tough compromises.
So instead of giving them one answer, the GA basically lit up the entire map of possibilities. It generated this set of things called Pareto optimal solutions. Just look at this table. It's not one answer. It's more like a menu of the best possible trade-offs. You see, you could go with solution number 2 and get incredible roundness, but you're going to have to sacrifice some smoothness. Or you could pick solution number 3 for fantastic smoothness, but guess what? Your roundness is going to take a hit. The algorithm doesn't choose for you. It just shows you what you have to give up to get what you want.
And this is what's so cool. It shows just how powerful the prediction was. To make sure it wasn't all just theory, they picked one of those trade-off solutions from the menu and actually ran the test in the real world. And the results? They were stunningly accurate. The actual physical part they made was almost identical to what the algorithm predicted. The system worked. It actually worked.
Okay, let's zoom out for a second. Let's pull back from the machine shop and look at the bigger picture here. Because this story, it was never really just about a piece of steel. It's actually a blueprint for how to solve all kinds of impossible problems.
The researchers totally proved their point. They concluded, and I'm quoting here, that this combination of tools can be used for minimizing the surface roughness and circularity error. Basically, they proved they had a reliable, repeatable method for cracking this very specific engineering puzzle.
But honestly, the real discovery here is the blueprint itself. This whole 4-step process is like a universal problem-solving engine. Think about it. First, you figure out what your conflicting goals are. Then, you use a smart design to get your data without wasting time. After that, you use stats to figure out what actually matters. And finally, you use these advanced algorithms to map out all the best possible compromises. And this isn't just for engineers cutting steel, you know? This is for anyone facing a complex choice. It could be balancing a project's budget against its deadline, or a company trying to balance profit against its environmental impact. Heck, even our own personal finances. That constant battle between saving for the future and living for today. So it kind of leaves you with this one last big question. What hidden tug of war is going on in your world, and what would it take to find its perfect compromise?